telling you that this chapter we're taking, or that we're doing, is incredibly foundational for the rest of the year. Okay? It's not a hard concept, but it's things that I just kind of need to lay out and tell you facts about so that you have it. And so it's important for you to get these facts so that you can do the rest of the stuff. So we're going to be talking about this thing called normal distribution and what that is. So of course, a distribution is, a shape of data. So we have different shapes of data. Remember we talked about shapes of data that end up being like this. Those are what? Correct. And then we've ended up with shapes of data that are this way. We've had ones that are like this. Okay. So we have different shapes of data. And we're going to be talking about this thing that ends up being normal shaped. And we're going to also find that this thing that's called normal actually has specific numbers related to it. Okay, so here we go. Furthermore, where we've done multiple chapters at a time, we've done multiple chapters to take up a unit. This is so important that one chapter is going to be its own test for this unit, okay? All right, so here we go. So the first thing, and you guys have got the slides there in your notes. So the first thing that I want to take a look at is data that is proportionate, and the proportionate probability where everything is the same frequency would look like this. Remember that this data going straight across is uniform. You remember that word uniform? Okay, so if it's uniform, then what that's meaning is that the amount of people that made, say this was a test score from 0 to 100. Okay, so the amount of people that got a 0 on the test is the same as the amount of people that, say, got a 50 on the test. Okay, so those are the same height. They had the same amount of people. If you envisioned this being a histogram, that got a 0 on the test as that got a 50 on the test, and, even got a 100 on the test. So, first question is that really reasonable for, say, test scores? Is that a reasonable idea? Okay, that is not reasonable for an idea for test scores. Now, some things it might be reasonable for. This is like talking about the average number of blinks that different people are making at different ages or whatever, then maybe those are pretty much the same all the way across. Okay, but at any rate, this entire distribution represents all pieces of data. And all pieces of data total up to how much percent? Okay, good. So this entire distribution totals up to 100% of the data. All right, very good. So now, let's talk about our chances of getting parts of this, multiple parts. Say, for instance, I want to put all of the pieces of data in a bag and see what's the chance that I reach into the bag and grab one of these pieces of data of a test score or whatever it is that got 40% on the test or less. So that would be this entire section. Okay? So we want to find out what the probability of finding a piece of data that is in this section. Okay, so that's where we're headed with this. And so what I would want to do, so you can visualize this amount. So I have it all. I have all the data in a bag. I'm going to reach in there, and if I want to get 0.4 or less, then I'm going to actually just, what's that chance going to be that I grab one of those? It's going to be 40%. Okay, and the reason that it's 40%, so let's talk about that, is because, and this actually is not drawn to scale, unfortunately. All of the way across here, it goes to 1. And the area of it is equivalent to 100%. So how would I get, what would I have to do to make this area the value of 1? How do I get a value of all of this section? So let's shade it. What numbers do I need for this whole section to have an area of 1? aka 100%. 1 squared. Very good. Now see, it's not drawn to scale, so that's kind of misleading. But this is 1, and if this length is 1, the base is 1, then what does the height have to be? It also is 1. Okay, so we are dealing with a very poorly drawn 1 by 1 square, okay? And so the area of this section, so this is kind of where I'm going with this, the area of this section equals the probability of getting those amounts. All right, so that's the key, that the area of this red section is the same as the probability of getting that value when what's in this square is 100%. Okay, so let's see another case where the shape is a little different. The shape is only the height of 1/2. Well, since the height is only 1/2, I still need to have 100% in this distribution. So then what's happening to this, the base of this? It has a value of 2. And that is because, of course, your 2 times your 1/2 is going to equal your 100%, okay, or your 1. All right, so next question. What is the probability of getting a value in this red shape, this red rectangle? How much? 60%? No. Okay. In this, so how did you come up with 30%? Okay. Good. If I take 0.6 and I multiply it by 1/2, what is that? This is 0.6. And you multiply it by 1/2. If I do 0.6 times 1/2, and I get 0.3, which is 30%. Very good. That's not the area of the red piece. That's the area of the white piece. Okay. So therefore, thinking complement, you're going to think 100% minus this 30% gives me how much in the red piece? 70%. Okay, good. What's another way that I could come up with this 70% straight away? Yes, because from 0.6 to 2 is a width of how much? So this section here is actually your 1.4 with a height of 0.5, and so therefore that's how you get your 1.4 times your 0.5, giving you 0.7. So there's 2 different ways, whether you are finding the white part and subtracting it from 100, or just straight out finding the red section. Okay, but at any rate, the area is equaling the probability of getting data in that section. Okay. Now, let's take a look at data that's more like real life. More frequently, our data in real life is not uniform like that. Frequently, we have a distribution that looks like this, where we have histograms, and our bins are 1 to 5. I don't know if you can see that, but 1 to 5, and then up to 10, and up to 15. Okay, so we have this shape. What kind of shape would you classify this as? Probably what? It's pretty symmetric and unimodal. Very good. Symmetric, unimodal. All right, now look here at this next one. It's the same data transformed. However, the bars in this histogram are not a width of 5 anymore. They are a width of 1. So do you see how they're skinnier bars? Now, I want for you to compare the shape of this top section on this one to the shape of this section here. How would you compare those 2 shapes there? Or what's the qualities of those 2 different distributions? Okay. How about just like the quality of like this blue line? How about that? The quality of the blue line. What? They're still unimodal. Okay, let's get away from those words. More what? It's more precise, yes, because I have it now in terms of ones. Does this look smoother and not as jagged as this? So I'm being able to be more accurate. Okay, so here's the idea. As these numbers, as these bins, the width of these bins get smaller and smaller and smaller. What if they were like a 100th in width? Then you get closer to a curve, a smooth curve. So it's kind of actually a calculus idea that as the bin width gets smaller, then you have infinitely many bars, and then they end up being totally smooth, like a normal curve. Okay, so let's talk about this real quick. I think probably the first thing on here to notice is it actually is kind of nice. This is pixelated, you know, just because of the graphics of it, but it almost can make you envision that each one of these is a histogram. And when you have all these histograms that are so small, it makes something that looks continuous, okay, and like a straight line. Okay, now, this right here is a formula that looks crazy difficult, okay? It is something that is, you know, you would put into y equals. It is a function that is used in calculus to say compute like how much this area is right here. Okay? You know, before, a couple slides ago, how did we find the area of those sections? Yeah, we did length times width. Very good. Okay, but on this, why can I not just do length times width on this? Well, yeah, because I got a curved top. I don't have the regular rectangle. Okay? That's where the calculus concept comes in, that this formula was used, and you integrate across that to find this area. And so we are not going to even have to touch that at all, because there are tables of values, there's our calculator, and you know, mathematicians have done all of the computing for us to be able to tell us if we know these amounts here, if we know those values, we can compute that area between them. Okay, so the good thing is we don't have to do that at all, so that's nice. Okay, so there you go. You can wipe your brow and be glad about that. So we have the normal curve. And the question I'm wondering is, how can you tell where the mean or the median is? Where do you... Are they both there at 0? It looks like it. Okay. Now, what would lead you to believe that they would both be there, Ernie? Because it's symmetric. And we know that when they're symmetric, then our mean and median are the same. Very good. Okay. And when we had done our little height activity in here to talk about standard deviations, we said that, you know, you're 1, 2, or 3 standard deviations out. Did we have anybody here at 2 standard deviations above the mean? I don't remember. When we did our height activity, you remember? Oh, yeah. This was our lower. Okay, we did not have an upper outlier. Good. But we did have a lower outlier. That was more than 2 standard deviations. So in a normal curve, most of the data is within 3 standard deviations. We typically in science consider something an outlier if it's less than 2 or above 2. We had already talked about that. But let's now address this idea. You already told me that the mean and the median are there in the middle. So here's my next question. What happens if this item right here changes? My first question is, what is that? Okay, it is a Greek letter, lowercase sigma, that represents the standard deviation. Now, the fact that it is a Greek letter as opposed to a regular S infers that this is a standard deviation for what? Good. It infers that this is population data, not just for a sample. Okay, so you remember that Greek letters are important because they're for the population, not just for your sample. Okay, so let's talk about this. I'm going to draw in red smaller standard deviations. Okay, so I'm going to make them half as big. So there's 1, 2, 3. Okay, so then let's go down 1, 2, 3. All right, so here's my question. What is going to happen to all of the data if I make the standard deviation smaller? It's going to what? Shrink up. Okay, that's what I'm looking for. You don't have to tell me technical terms. It's going to shrink up. It's going to condense. It's going to squish in. Okay, I got that. Well, you have the same amount of data, so if I'm squishing this thing in and making it smaller and skinnier here, then how do I still fit all that data in under the curve? What's going to happen? No? Okay, think about, I wish I had a real thing to demonstrate this with, but I just kind of came up with this idea this morning. So think of, say, like a water balloon or something, say a water balloon that I have in the shape. Yes, if you squish it in, then what's going to happen to the water? Yes, it'll get taller. Very good, thank you. So if I have this skinnier, then it's got to be taller so that the same data is in that area. Or so the same amount of area is still contained there, still 100%. Good. All right, let's talk about the opposite effect. What happens, I'm going to do this in green, if I have a larger standard deviation? Okay, then what's going to happen with that? Okay, it's going to flatten out. It's going to spread out. So it actually becomes wider out here, shorter, and it's wider out here. Very good. So this green curve is representing a larger standard deviation. The red curve is representing a smaller standard deviation than the blue data. Okay, very good. Now, in summary, so it's kind of just like what we've talked about here so far. We know that our normal distributions are symmetric, talking about mean and median and all that kind of stuff. They are unimodal. We also call them mound-shaped. But if they are specific, following specific math formulas, then they are called this thing called a normal distribution. You told me the mean and the median were the same. This thing right here represents the mean. It's a Greek letter mu. So therefore, that implies the mean of what? The mean of what? Come on. Good. Because this is your lower case sigma. So these are letters that represent population, and they are parameters. We've said that like first chapter we did. So you may remember that. Population parameters question when they were Latin letters and they were representative. So there's the mean of a sample, and here's the standard deviation of a sample. Do you remember what they were called as opposed to population parameters? They were called sample, what? They aren't sample stuff. Sample statistics. Okay, so remember that when they were populations, they were called parameters. When they were sample data for the samples or information, they're called sample statistics. Okay. Moving on. All right. Normal. What's normal in statistics? Okay, this is when we're going to use, it's going to be more representative of our real data. Okay? We're just like, you told me the test scores, that flat square distribution, that's not a good representation of test scores. That's not what real data looks like. Real data is more looking like this. Okay? Now, we are going to use this thing so much. That's why this is such an important chapter, because this concept that making inference about testing items is the entire second semester of this course. So you have to know this normal model backwards and forwards. Now, it's important to note that many items are not normal. So you may wonder, why are we then going to concentrate this entire year on the normal model if a lot of things aren't normal? Okay? And the reason for that is we will learn skills how to turn things into something normal. If it's not normal, we'll learn skills how to manipulate it to make it normal. Okay? Additionally, in order to tackle items that are not normal, you are in an upper level statistics class that requires calculus to do those computings because it's not already done for you, like the normal curve is already done for us. Therefore, we don't tackle any of the other ones. Okay, here we go. So let's get the math on the normal curve. 68% is what's between one standard deviation up and one standard deviation down. When we did our height, do you remember how normal was our class? I can't remember. I wish I had our data.
3.8.
No, were we pretty close to having 68% within one standard deviation of the mean? Pretty close. I don't remember. Okay. Do you recall how much data is within 2 standard deviations? 95% should be within 2 standard deviations, and 99.7 should occur within 3 standard deviations. So question, how much data is more than 3 standard deviations out? 0.3%. Okay. How do I get that? Let's come up with that. Yeah, 100 minus 99.7. That gives you the leftover 0.3%. Where is that leftover 0.3% on this picture? Yeah, this little piece here and this little piece here. And if that 0.3 is split between those two pieces, how much is in each one of those little pieces? Thank you. 0.15%. Now, amazingly enough, I mean, this is crazy. You will not even, I mean, it's just astronomical. I don't have a clue how this person came about with this. But this is known as the 68, 95, 99.7 rule. Really it is. Literally. Yeah, I know. Now, I will tell you, in past generations, so like my dad who's an engineer, when he would do things, he referred to it, and they grew up and learned it as the empirical rule. So you need to be familiar with that word, because when you go to college and you're dealing with a professor that has the older language, or you're dealing with psychology, biology, any of those things, they may reference the empirical rule, but you need to know that it's the same thing as the 68, 95, 99.7 rule. Okay. So, I want you to figure out how much data, what percent of data is in each one of these sections. I'm not going to tell you how to do that. You're going to figure it out. So I'm going to clarify what I'm asking again. If this entire amount from here to here, and I don't want you to say your answers out loud because you're going to just work in your little groups. If this entire section is 68%, then one of the things you're going to be finding is how much is in each one of these items. Furthermore, you're going to have to be finding how much is in this piece and this piece. I will tell you those two green pieces are the same amount because of symmetry. You're going to figure out how much is in each one of these pieces here. So from 2 to 3 standard deviations. And furthermore, and this is the piece that my last classes have left off, I want to know how much data is also out here. So I'm going to let you go and do that. And when you have it, you tell me, and I'll look at it, and you get a stamp if you have it correct. So do that. I could have easily just kind of come up here and hammered through talking through those numbers, okay? But then, it would not have like gone through your brain, and it would not have sparked some electrons or whatever and helped you to figure out what those numbers are. Okay, so if I sat here and I said, oh, you do this and you subtract this, la 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 la, okay, then about 3 of you would kind of follow that and the rest of you wouldn't. So now that you guys have all your data in there, let's actually put those in there on this page. So you told me that, of course, there was 34% here, 34% here. How much were in these other sections, these ones next to it? 13.5%. Okay, here is your 2.35. Okay, now, the next piece of vocabulary that I want to walk you through is this thing called percentile. Have you ever heard of something like you're in the 75th percentile or that kind of stuff? Okay, percentile references the area below your mark. The area below your mark. So if somebody is in the 16th percentile, then that means that this area below this piece of data is 16%. Okay? And of course, being at the mean, you're at the 50th percentile because at the mean, you have 50% of the data below you. Okay? Likewise, how did you come up? How is this number of the 84th percentile achieved for this value right here? Add what? So 50% plus this 34% is how you achieve this 84 percentile. So what percentile is this mark right here? Yeah, 97.5. Very good, because if you added 84 plus the 13.5, then you add up, then you come to your 97.5 percentile. Okay, good. So percentile is that area below you. Now, let's get into a real problem here. Assume the heights of college women are normally distributed. I would think that that would be more likely than having data like this. I don't think this is reasonable for heights, that there's the same amount of people that are this tall as this tall and as this tall. So I think a normal distribution is more appropriate for the heights of people. So here we have college women heights, and the mean is 65 inches, and the standard deviation is 2.5. I want us to correctly label this guy here. So first of all, what is the information that this picture is about? Heights of college women, good. And that is in inches. Okay, good. So what is going to be here at the mean? 65. Now, what if you were one standard deviation above the mean, how tall would you be? How did you come up with 67.5? Ah, because one standard deviation up is 2.5 inches higher. So fill in the rest of those right now. Right now. Okay? Okay, so are you just adding and subtracting 2.5 inches? Alright, and here's what you got. Okay, so those are your inches. Now, in reference to this data, let's see, what percentage of women are going to be taller than 65? Correct, because that's at the mean. Good. Okay, so you guys have these slides, so fill those in as we go. I know there's some quick, easy questions here. Next, what percentage of women are going to be shorter than 65%? Oh, sorry, not 65%, 65 inches. 50% of the college women. Good. Next, how about between 62.5 and 67.5? How did you know that? Because of the empirical rule. Right, one standard deviation out. Good. Next, two standard deviations out. Okay, 95% of college women are going to be between those values. Now, you get a little bit different. It's not straight out off of the 1, 2, or 3 standard deviations out, so we're going to kind of combine some things. So, I don't want you to say it out loud, but think right now in your brain, how are you going to find that value there? Say it out loud. Okay, so did anybody add to get this value? Add values to come up with your total? Okay. So question, what did you add? What's here in the middle? Okay, 68. And this here is, okay, how did you know this was 13.5? Okay, well, earlier in the day or earlier in the class, whenever we had done that. Okay, so total that makes, I think it's 81.5. Okay? All right. How about this one? What percentage of women are shorter than 70 inches? Okay, so figure that out. There's actually multiple ways you can do this one. I think we'll get some more different ways of solving on this problem. So do that. many of you added to come up with your values? Added. Okay. That's probably most common. Adding. Okay, so let's see, what did you add? Here, mean down is how much? Alright. Mean down to 50%. What's this one section here? Okay. And then we just said this one from 1 to 2 standard is? Okay. If you add all those together, then what do you come up with? Okay. So if you are 70 inches tall, then you're in the 97.5 percentile. You're taller than 97.5% of college women. Okay, now, question, anybody do this by subtracting? Ooh, good. Okay, I want to know, there's even a couple ways to do it there. Richie, how did you do yours? Okay. Okay, gotcha. He added those two sections to get 2.5, and then he subtracted that 2.5% from 100% to get 97.5%. Okay, any other ways on that? I personally kind of remembered from 2 standard deviations out, right here, I kind of remembered from this that if the middle's 95%, then you split the 5%, and that's your 2.5. So I didn't even really think about adding those two pieces together. I just thought of the 95, giving me 2.5 there. Okay, but anyway, those are all good. All right, so next we are going to see what happens when we now do not have a standard deviation that's on a whole number standard deviation. Everything that we have done so far has been just like straight up 2 standard deviations up, or straight up 1 standard deviation up. But guess what? A lot of the data is in between there. And this is an example of that. So what happens if the whole number standard deviation is not what we're dealing with? Okay. Let's see if we can't figure that out. I'm going to let you discover this by this example. So pretend like we're 5 weeks into class. This particular girl, Ileana, had taken she goes to Lanier High School, and she had taken a Chapter 1 test, and we had just also taken that same chapter test. Thankfully, they were using the same text as us, so we were all kind of like in the same place. So, at her school, she got 61 out of 70 points on their test. But at our school, it was out of 100 points. So I always relate that to our 100-point scale. So, how am I going to figure out what score she should receive? Now, the way that you have done in your whole math education would be what? Yep. 61 over 70 is how much over 100? Okay? This is the proportionate method. This is going to happen if everything has the same value and there were the same amount of zeros as 50s, as 100s, as 61s, or 61s is here. Okay? Is that what's probably happening on these test scores? No. These test scores are most likely going to be more normal shaped. So therefore, we are dealing with something that is pictured more like this, not that way. Therefore, you cannot just do a straight up proportion. So, let's get some facts and then figure out what to do. So here's the facts. I called Lanier High School because this is actually really the way that it works, you know. So I called and I talked to their stats teacher, and I found out that on that test, the mean at her school was a 50.5. So right now in your brain, she made a 61, so we know she's already what? Above average. Good. But on our school, at our school, the mean was 77.2. Okay, standard deviation-wise, their standard, if they have a standard deviation of 8.8 and we have a standard deviation of 9.7, what can I say about their data as opposed to our data? Less varied. Nice. Nice. Less varied. Okay. So the question is, how can we relate those two things together, keeping the distribution of the grades in mind? And so I'm just going to pause right there and let you think about that. Your hint is that this is where that idea should come from. So think about it. I'm not telling you. I'll pause. because this may take. So we're going to put both of the data on this at the same time. So I'm actually going to kind of make two lines here. So I'm first going to put her data on the chart. All right, so here we go. The mean for hers was 50.5. And then they had a standard deviation of 8.8. So what's the next one up? You know I can't add, so here I go. So, yep, 59.3. And then the next one up from that, I think it was like 68.1. Okay. I pretty much could stop right there because I know I've addressed where her value is. Her value is located where? At 61, which is going to kind of be in which section? Between 1 and 2 standard deviations. So how about right there? I think that's about where her 61 could be located. All right. Now, we had the good idea. Sarah had a good idea of putting this in terms of overlapping both of the sets of data. So let's put our data below it and then see what that does for us here. So we have a mean of 77.2 and our standard deviation is 9.7. So let's say this is 86.9 and the next one is 96.6. Okay, so I have an idea. Okay, so it's going to be somewhere around above the 86.9. Now, it is not okay just to guesstimate. We are going to do this exactly because we got to learn this process. So, at this point, how can I make the connection between where it is on one and where it is on the other? Percentile is a good idea. You have to figure out. Now, how do you know? You don't know the percentile because you don't know the whole standard deviation. Because this isn't like exactly at 1 standard deviation, so I can't just say it's in the 84th percentile or something. No, it would be the same. It would be the same because it's a normal model. So the percentile would be the same. So I can't find percent. Should I pause? Okay, I'm going to give you a hint just because I don't want this to us not be able to get through for your homework. I need to know how it's related to the mean. How can I figure out how it's related to the mean? I need to kind of get a concept of this distance, but I can't just say like that flat out distance, but I need to get it in terms of how many what. Yes, yes, yes. Very good. So here it is. I need to find out how many standard deviations this score is above the mean. That is the key to the whole thing. Very good. So, let's do that. All right. So her score is 61. How do I compare it to her class information? Compare it to the mean. What do you do? What? Subtract it, I heard. Subtract what? Okay. This is how far hers is away from the mean. And that amount is 10.5 points. But it needs to be in terms of standard deviation. So I'm going to, divide it by their standard deviation. And that will tell me how many of their standard deviations it is above the mean. So divide by their 8.8, and that number is 1.19. So guess what? Her score is 1.19 standard deviations above the mean. That's how she got a score of 61. So let's relate it now to our class. How? The mean, and I need to go 1.19 standard deviations up. What do you think? Good. So, going to add to our mean 1.19 of our standard deviations, and our standard deviations are 9.7. So that comes up with a value of 88.7 something, so I would be giving her an 89. Okay, very good. The key is relative to the mean, and that's called a z-score. So if you look in your notes, the relative position is called a z-score. You did this. Her score minus the class average divided by that standard deviation to see how many standard deviations it was away from the mean. So the definition of z-score, which you have on your slide, is the number of standard deviations away from the mean. Now we have a few minutes to do this last example here. Suppose that a student has taken 2 quizzes, and I want to compare how well they did on one quiz and the other quiz. The key here is this: relative to the rest of the class. In other words, relative to the mean for each one of those quizzes. So let's look at the data. Here we go, the information. On the first quiz, the mean is 32. On the first quiz, the standard deviation is 8. And this student got a score of a 44. So automatically I know that the student's score is what? Above average. Let's see how much above average. Let's find out how many standard deviations above average. So that's a z-score. Okay? Let's see how far their score is above average. Their score of 44. Find how far it is away from the average in terms of standard deviations. That comes out to 1.5. Now you could do that math there. Okay, let's see how well this student did relative to the rest of the class on the second quiz. So, the student got a 28. Student got a 28. Now the class mean was a 23, and the standard deviation was 3. So let's find that z-score. So tell me my formula here. Ready? What's first? 28 minus 23 divided by the standard deviation of 3. That comes out to 1.6 repeating. So, relative to the rest of the class average, which quiz did the student perform better on? Yay! Why the second one? More standard deviations above the mean. Good. So this person did better relative to the class on that one. Okay, this next one I don't know if we have questions, time for, but go ahead, Ernie, what you say?
Is there like units in
Ah, such a good question. That's a stamp, mister. Yes, okay, listen, this is so good, and we're going to talk about that tomorrow. There is no unit for standard deviation. It's standardized because look what happens. When you have a unit here and you have this difference and you have the unit here, they cancel, so it's a standardized value not related to units. So good thought. Now, you do have your homework, Chapter 6, Part 1. I'm going to tell you that quite a bit of it is review. I also think these answers are quick and easy, so although it is a page and a half, it will not take you forever. It'll be pretty quick answers on that. Very good.